Hi, welcome to the Kill the Bit game for the ALTAIR computer. Oh, wait a minute, it doesn't look like Kill the Bit. It appears to be an old-fashioned flight simulator. Ah, here it is in all its beauty. Unfortunately, I do not have an ALTAIR 8800 nor clone, but a simulator. You can find the link of the software in the description. I have previously loaded the game. It's already running. As you can see, there's no keyboard or screen, just LEDs and switches. The goal is to catch the lit bit with the corresponding switch. You have to toggle the switch back fast enough, otherwise another bit turns on. Dean McDaniel wrote this game in 1975. The source code is listed below. But before you leave me for the flight simulator, I want to show you the gameplay. You won't be disappointed. So on the real device you don't have a problem to quickly toggle the switch, but in the simulator I'm not fast enough, because you can't toggle it. You have to click here for turn it on and a bit below to turn it off. So let's give it a try. Missed the point here. So now we have a lot of bits here. Makes no sense to continue. Let's cheat a bit. So at memory address 6, 4 and 2 is 6. Examine. I will replace the existing value, which is 84214 E in hexadecimal. I will replace it with 2. 2 should be fine. So at address 6 there's now 2 stored, resetting the program counter and starting the program. So now it's a bit slower. So if I toggle on the wrong place, it has added, well, I've even waited too long, several bits. So let's try to get rid of them. I have to click below again. So I think I have to click here for switch and try with this one. I was too fast now. So, every bit killed. I told you, you won't be disappointed. There are 3 reasons why you're still here. The first one, you are speechless. The second one, you just like blinking LEDs. Or you are interested in the source code. So let's go back to the original source code. I've just added the Z80 mnemonics for those of you who are more familiar with Z80 instructions. And let's start with the first command. The first instruction is to initialize the counter, so setting the CPU registers H and L with 0. The next instruction is to set up the initial display bit, so that's the most left bit, that's why 80. Let me show it in the simulator. So I'll stop it. This bit has to lit up, and if you check here, that's 8, 4, 2, 1, 8, 4, 2, 1. So this part is the 0, and this part is the 8. I hope that makes sense. That's why Dean used D for display. I'm just kidding. So, next instruction, higher value is faster. So I've already modified it from 14 to 2. That's a 16-bit value in register BC. And the next one, display bit pattern on. That's an interesting one. So, loading accumulator with the value of a memory address which is specified in the double register DE. So why this? Let's have a look at our front panel. So these upper 8 LEDs represents the data bus. And below we have 16 LEDs which represents the address bus. So there's our answer. This 8 bits are the upper addresses of the address bus, and these 8 bits are the lower address of the address bus. So we want to use the upper 8 bits. Again, this instruction will set the address bus with the values of registers D, E, and load at that memory address the value to the accumulator. We don't care about the value, we just ignore it. We don't care about E, because that's a low byte representation of the 16-bit address, but we care about D. That's the upper byte representation, and it's already specified here. So it will lit up the most left LED. Let's have a look in the simulator. It's at address 8. I will change back, I will modify the value of BC. So at address 6, I will put E back in. So E is 14, 8, and 4 is 12, and 2 is 14, and deposit. So putting switch down, quick test, resetting, run. So now it runs at normal speed, but we're going to do a single step. So we're going to address 8. Single step, single step, single step. At the address 8, we have the instruction 1, A. A is 10, 8, and 2 is 10. So let me execute it. So now the CPU has set the address bus to the value of the corresponding, to the value of register DE. So this one is the address, is the register D, represents register D, 8, 0. And this one represents register E. There was a value 4 and 2, 6, 1, 2, 4, 6, 4. 6, 4 was in register E. We don't care about it, just, yeah. Let me execute the next instruction, address 9. So the CPU fetches the next instruction. At address 1 and 8 is 9. And there again is 1A, there's instruction 1A. So with the execution of that instruction, it sets the address bus again. Why did Dean put 4 times in a row the same instruction? Well, that has a reason, because otherwise you wouldn't see clearly the bit moving around. Let me show it to you. So this is a normal 4 times instruction load the accumulator. At address 11, 8 and 2 is 10, and 1 is 11. Examine. So we have our 1A here. I will overwrite it with, wait a minute, is that 1A? Yeah, it is 1A. We'll override it with 0. 0 means no operation. deposit, resetting, and run. So you see the LED is a little bit dimmed because he's only executing it 3 times. Okay, let me override at address 10. Also the 1A with no operation. No operation is 0. So deposit, setting, and running. You can barely see it now. At address 9 I will also eliminate the 1A. Deposit, and so you can barely see it here. The next command is an addition here, an addition of 2 16-bit number. So we will add the 16-bit number of BC to the number of HL and put result in HL. And as long the result fits in HL, there will be no carry. So it will jump on non-carry to the beginning. It will loop until an overflow, a carry, occurs. So if a carry occurred, it will jump to the next instruction at address 10 here and input data from send switches. These 8 switches here are the so-called send switches, which you can use for input data in a program. Let me check at address 10. There's a command D and B. That's a 2-byte command. So with the next command there's a FF. All the switches are down, so the result will be all data bits cleared. Okay, let's do it again. This time I will enable this switch and enable these 2 switches. So, single step, you can see here the result, 1 switch up, and these 2 switches are also up. The command input will put this value in the accumulator. The next instruction is exclusive OR D. So we'll do an exclusive OR with the accumulator, so with your switches, and with D, that's the display. Just remember, so if they are equal, that's 0. I mean, that's also 0. If the bit is different, like 0, 1, that's a 1, or 1, 0, that's also a 1. So if you missed a bit, so there's a difference, and it will add another bit to it. And if you hit the bit with your switch, the bit is cleared. 1 exclusive OR 1 equals 0. That's the whole AI. That's a one-liner. And the next command is rotate display bit 1 bit to the right. So if it arrives at the lowest bit, it will turn back to the highest bit. And here we are saving the accumulator back to the display register and jump to the beginning. Starts over again. So that's it. Thank you for watching, and see you. Bye bye.